Hey everyone, and welcome back to another video from the Waste Tutor. In this video we're going to be going over computation and properties of derivatives. It's the second topic of the introduction to differential calculus, and we're going to be having a look at introducing a couple of rules that we can use for differentiation, and kind of building on the first principles approach that we developed in the previous video. So over the course of this video we're going to be having a look at numerical differentiation techniques. So having a look at substituting specific values in as the point approaches, as our secant approaches a point. So that was the first principles approach that we looked at, and using those techniques we can kind of estimate what the value of a derivative is at a certain point in a function. We'll then have a look at variable rates of change of nonlinear functions, showing that the gradient of a function changes over time if it's nonlinear. Linear functions, they have a constant gradient because obviously it's a line. We'll then be having a look at the power rule, which is the predominant differentiation derivative rule for year 11, and you kind of get introduced to the product rule and the quotient rule in year 12, and as well as the chain rule. But for now we're only going to be dealing with the power rule. We'll also be having a look at how we actually derive this power rule using the first principles limits approach. Then we're going to be having a look at properties of derivatives, seeing that a derivative can be considered a function. We're going to be having a look at some of the linearity properties of the derivative, which allow us to finally calculate derivatives, compute derivatives of polynomial functions. So let's get straight into the video. Okay, so the first thing I'm going to go over is a branch of calculus, which isn't exactly really the more formal form, but more of an applied form. It's numerical estimations for limits and for integrals and for derivatives. For the purposes of this video, we're talking about numerical estimations for derivatives. And so what I mean by numerical estimations is, if we remember from first principles, the way that we compute a derivative is by taking a point along the curve, f of x, this is y equals f of x, and taking another point q, and essentially what happens is we calculate the gradient of this tangent as the tangent steadily approaches closer and closer to the point. So that is as q approaches p until q is superimposed over p. And so the way that we refer to that is we talk about the limit of q tending towards p, or more specifically a point x and a point x plus h, and we evaluate the limit of this gradient of the secant as h tends towards 0. We can estimate what the value of a derivative is by plugging in specific values, specific x values for points along a curve. If we consider y equals x squared, for example, and let's say we want to evaluate what the derivative of the function y equals x squared is at the point x equals 1. We want to find the derivative. What we're going to do is we take our graph, we consider a parabola, y equals x squared. We consider the point x equals 1, which corresponds to a y value of y equals 1. And we can consider any point along the curve. Let's say we pick the point 2. And at 2 we know y equals 4. So at this point we have our value of x that we're choosing. We have a value 2 we've selected. And we are trying to calculate what the limit is as h tends towards 0 of f of x plus h, or maybe we'll label this as h, then h is 1. Okay, so if we have an increase by 1 here, then if we want to calculate the gradient of the secant, we have in this case 4 minus 1 divided by 2 minus 1. Which is 3 divided by 1, which is 3.
Okay, and so this is an estimation for the derivative. It's not a very accurate estimation because it's clearly a very different gradient compared to the tangent at this line, but it's our estimation. We can then come a little bit closer. We can go to 1.1 rather than 2. So in this case, our h decreases to 0.1. We go to 1.1 instead, which corresponds to a y value of 1.21. So 1.21 minus 1 over 1.1 minus 1. And if we calculate what this is equal to, that will be equal to 2.1. We can then go even closer, go to 0.01, and this corresponds to a value of 1.0201 take 1 over 1.01 take 1. And this corresponds to 2.01. And so as we continue so on and so forth, we realize that our limit starts approaching 2. And we'll have a 1 value kind of lying there. But numerically, we can estimate the value of the derivative of y equals x squared at the point x equals 1 as 2. And so this is our numerical estimate for that function. Something I also want to take note of is the fact that the rate of change of a function changes for a nonlinear function depending on what x value it is. For this quadratic function, the rate of change at the point x equals 1 will obviously be different to the point where x equals 2. Because if we consider our graph, and we have our parabola here, at the point x equals 1, our tangent may be like this, whereas here, at x equals 2, our tangent is significantly steeper. And so if we consider a non-linear function, we can see that our gradients change over the course of the function. And there's important points here where the gradient is completely 0, here where it's also completely 0, and here, here, here. Here, the tangent is steadily decreasing until we approach 0, becoming more and more negative, and here we start approaching 0 again before becoming steadily more and more positive. The main point we should understand here is that the rate of change, or the tangent drawn to the curve, changes according to what x value it is for nonlinear functions. The next thing I want to introduce is something called the power rule. What the power rule says is that the derivative of a function ax to the n will be equal to n ax to the n minus 1. That is, if we have x cubed, what happens is we drop the 3 down, 3x, and this subtracts by 1, so we get 3x squared. And so this is a bit of a faster way of computing a derivative compared to the first limits approach. We can also prove that the power rule works for non-negative integers. The proof for negative integers is a bit more difficult, and it's outside of the scope of Year 11 methods, but there will be some YouTube videos online that you can have a look at if you are interested. The way that we prove the power rule is by using first principles. So if we have our d dx of ax to the n, we know that by first principles it's going to be equal to the limit as h tends towards 0 of ax plus h all to the n, take ax to the n all over h. And so here we get the limit as h tends towards 0. We know that this function here can be expanded according to the binomial theorem. That's something we learned earlier. And it can only be expanded according to the binomial theorem if it's a non-negative integer. That's why this proof only works for non-negative integers. So if we expand that out, we get a x to the n plus n choose 1, x to the n minus 1h plus so on and so forth, n minus 1 x h to the n minus 1 plus h to the n, take a x to the n all under over h. Okay? So if we look here, we have an ax to the n value, we have an ax to the n value. Both of these values are equal to each other. This is subtraction, so they cancel out. And as a result, we have the limit, as h tends towards 0, of a n choose 1 x to the n minus 1 h. This can be written as n because n choose 1 is n. N choose n minus 1 is also n, x to the h n minus 1 plus h to the n, all over under h over h. We can also take this a value out the front of the limit because it's not influenced by this h tending towards 0 at all. So we have a, the limit as h tends towards 0, of n x to the n minus 1 h plus n x h n minus 1 plus h to the n, all over h. We can now cancel all the h values out. So we are left with h tending towards 0 of n x to the n minus 1 plus so on and so forth, n x h to the n minus 2 plus h to the n minus 1, and we have cancelled out the h's now, so we can move this down. I'll just leave that there. So now that we have our h's cancelled out, we can let our h tend towards 0, cancelling everything else out other than this value here because there's no h associated with it. And so we're left with ax to the n, anx to the n minus 1. And so this is the derivative of ax to the n. And so we've established the power rule using first principles. Alright, so the next thing I want to do now is understand the concept of the derivative as a function. If we had a look at the power rule, we saw that the derivative of ax to the n is equal to ax to the an x to the n minus 1. And so if we consider a function x cubed, and the derivative of that, we get 3x squared. That is, we have our n drop down to become 3. So this is our n corresponding to the n, with our 3 corresponding to 3. And we have the 3 decreasing down to 2 as well. Okay, and so we can consider this as a function equally as well. So where our initial function x cubed would have looked something like this, our 3x squared will look like a parabola, something like this. And so we can graph the derivative as a function just as well as we can graph our original function on a set of Cartesian plane. Another important thing is the linearity properties of a derivative. If we're trying to find the derivative of x cubed plus x squared, for example, we can equally write that as d dx of x cubed plus d dx of x squared. This is one of the linearity properties of derivatives, and it's probably the most important linearity property in differentiation. So if we want to differentiate x cubed plus x squared, we just differentiate x cubed to get 3x squared. We differentiate x squared to get 2x. And so we've differentiated. This is the derivative of x cubed plus x squared. And we can plot that on a set of axes. What these functions tell us here is the value of the gradient of the tangent drawn at any point along the curve. For this function here, this tells us the gradient of the tangent drawn to the curve at any point. So if we have x cubed plus x squared, we know that the gradient of the tangent drawn at the point x equals 1 will be 5, because we can plug in 1 here to get 3 times 1 plus 2 times 1 is equal to 5. And so if we have x cubed plus x squared and it looks something like this, and we're looking at the point 1, maybe it looks something a bit more like this, maybe. And we're looking at the point 1. We know that the gradient here at the point 1 will be equal to 5. The gradient of this tangent will be equal to 5. That's what this derivative tells us. So we've had a look at the concept of the derivative of a function. We've identified and used linearity properties of derivatives. And we've also calculated the derivative of a polynomial function, because this here is a polynomial function, and we've been able to calculate the derivative of it. So that takes us to the end of this video. We estimated numerically the value of a derivative for simple power functions. We looked at how rates of change for nonlinear functions. We established the power rule using first derivatives for non-negative integers, and just trust that it also works for negative integers and everything else. You just don't need the proof. Next, we also looked at the concept of the derivative as a function. We saw that there are linearity properties associated with the derivative that allow us to calculate derivatives of polynomial functions. Now, the important thing is that you get a bit of practice with this in your Sadler textbook. If you have any questions, make sure you're putting those in the comments section. And we're almost done with the Year 11 Methods course, so stay tuned for the next couple of videos being released soon.